the curvature of space-time being infinite, right? I believe that's what he said. That's what would occur in a singularity event, and so on and so forth. But to me, what does that mean? What does that mean? That it would be meaning that because it's in like some type of thermal equilibrium state, does it like that nothing is supposed to happen as a result? Is it that it opens up more questions more than it answers? Like, is it because at that point we would then have to ask, what is it that set it off?
As
right?
far as
what is it that set it off?
Specifically in what regard? Like,
Well,
because
I'm not even exactly sure that I understand thermal equilibrium completely, but at the very least, I know one of the things that he used, one of the terms that he used, he definitely said that he said that a singularity event would describe a scenario where things are infinite. Here's what he said. He said a scenario where things are infinite. Well, that's the question that I have. What does that mean? Like, what does it mean things are infinite? Like time, or like?
It would mean that. Okay, so I'll start there. So I've spent a lot of time redefining terms because I was in the same spot that you were in. I was studying physics and quantum mechanics, and doing an introduction level, and then the analogies that they use just didn't make sense. Like, virtual particles are described as being coming into and out of existence, which is basically a violation of the conservation of energy. So the more you listen to the physics being explained at the higher level, where you don't have the comprehension of the math, the more contradictory it sounds. So what I started doing personally is I started redefining terms. So infinity means basically it means a magnitudinal force. It's basically the best way to think of infinity is a car accelerating, right? So when you're in your car and you accelerate, you know that you're going to accelerate all the way until your car reaches the maximum velocity, right? Well, I should say you're going to accelerate till your car reaches the maximum speed, right? Velocity is a rate of speed is the rate at which speed increases over time. That's what velocity implies, right?
Okay.
So infinity is the same thing. It's a value that increases over time, where time is undefined. The length of time itself is also described as a progression toward the future that is exponential. So it's going to exponentially, you're going to have 1 day, then 2 days, then 4 days, then 8 days, then 16 days, then 32 days, and you're going to continue in that pattern for forever, beyond forever. And that's what infinity implies. But there's another condition for infinity that a lot of people don't really know about, and that's the continuum. And the continuum is something that I created for myself. What the continuum basically means is you have an infinite progression in a finite volume. Does that make sense?
An infinite progression and a finite what?
In a finite volume.
Volume?
Yep. So the space, the container is finite, but the action taking place is infinite. Now the best description of that is the proton and the electron interaction. The electron, if it doesn't fly out of the atomic nucleus, the electron has an infinite progression around the proton. Its orbit is infinite, but its position in space is finite, right? So now you're able to comprehend a form of infinity. Now you have actually a piece of infinity that you can tangibly comprehend, because you have an electron in orbit around a nucleus, and the electron's orbit is infinite, but the nucleus of the atom is finite and actually something tangible and physical. So
right. Without taking quantum mechanics into account, right?
Right. Without having to take that leap. So
Right.
So you can see in that perspective, what happens with the birth of the universe, they say the singularity is infinite because it has to be all aspects of everything compressed into one state. But to me, this defining a singularity as infinite is flawed because the singularity is eternal, and things that are eternal are not infinite. They're only infinite in changing, in the same way that an atom with an electron orbiting around it can be described as infinite, but is actually just a continuum. The universe is not infinite, it's a continuum, but it occupies infinite space. So space as we perceive it is infinite, but the capacity to fill that volume is done with a finite form of matter and energy. So it's the matter and energy that's finite, not the universe. And that's what the singularity describes. The singularity describes infinite energy compressed into zero dimensions inside of an infinite vastness of nothingness, because we say that space as we know it didn't exist until after the Big Bang, right? So before the Big Bang, in dimensions was undefined as we perceive it, and that's what the singularity was. And that's kind of the approach that I took. Instead of trying to correct the misunderstanding of physics, I just corrected my perception of it without changing it. I didn't change it. I just tried to perceive it, and that's kind of the approach that I took. That's like a lot of the things with the Big Bang is broken because of that. Because like I was telling you before, you have to change the laws of physics to reach a singularity. Because you technically can't put a proton in zero dimensions, right?
Right.
If you can't put a proton in zero dimensions, then how can you put all the matter in the universe in zero dimensions?
Right.
I mean, like that's just, I'm just being realistic. Like, that's just common sense. So what you have to say is that matter and energy cannot occupy the same space. So all of the matter that formed the universe, that was compressed into a volume that will be defined by all of the matter of the universe as close as it can be to each other without violating the law of matter, where matter cannot occupy the same space. A neutron star compresses atoms very close to each other, but it doesn't violate the fact that protons cannot occupy the same space and neutrons can't occupy the same space. So the singularity in my mind is the same thing. It's a huge volume in relation to the infinite, to the vastness of our universe. But compared to the vastness of our universe, it's almost as if it has no volume at all. Because if you took all the matter in our universe and compressed it down to its absolute, like a super solid, basically. That's when I think of the singularity, that's what I see in my head. A super solid. All of the matter in the universe, all contained into one solid, unbroken chain.
Right?
Yeah.
So like the size of an electron or smaller, right?
Right. Yep. But all of the energy, all of the matter is there. All of the protons and the electrons are fused together to form neutrons. It's like a state of nothing but neutralness. All of the electromagnetic force is bound together in a state of equilibrium, and it's all held together by gravity. And something changed in the force of gravity that allowed expansion to occur. Some variable tipped.
Oh yeah, for sure.
Yeah, some variable tipped, and electromagnetism occur. You know, this is what would be ironic. Imagine a bunch of infinite super. We'll call them. We'll call them. We'll call them singularities. Imagine a bunch of infinite singularities, all one dimension in diameter, because you can't have zero dimensions. To say that the singularity occupied zero space, that's not right. So we'll say one dimension in diameter. They all of these singularities are all one dimensional diameter. They're all perfectly balanced in perfect harmony. They're moving through existence, because that's the way I see it. Our universe is inside of existence. So all of these point-like universes are moving through existence, right? They come close enough to each other or collide with each other in such a way that they disrupt the gravitational force, and that causes inflation. That's how I see it. That's what caused inflation. Because you have our universe flying past another universe, like two protons flying past each other, and they get close enough to each other that their gravities interact extra dimensionally. It causes a disruption, and then they expand, and that's inflation. And that's literally what causes inflation. To me, that's how I see it.
I mean, that's not a model that's see, even if you're speaking of it in different terms, in different languages, though, it conveys at least a very similar idea, in that quantum physics also depends on two or more systems, right? Two or more systems that get entangled with one another, and then cohere, right? So it's almost impossible to work with a one thing without another somehow in one way. Even in quantum physics, as weird or as many liberties as quantum physics allows, it's still dependent on like this other factor or element, whatever it may be. But there's something else there that it depends on it in order for there to be an entanglement that perhaps may have brought about space-time as we know it, right? It is because of something, two elements, two things two systems that somehow became entangled with one another.
Yep.
So the real question is, what are those two systems supposed to be? At least in quantum field theory, that would be the question: is, well, what are those two systems that we are suggesting brought about the Big Bang? And I think that's where the state of the art right now just has not had an answer yet, right? But well, I mean, they're definitely working on it, and that's definitely one thing. But as far as like, let's take a paradox that I also have a question for, and that is in regards to space, right?
Mm-hmm.
Like when to me, it's such a paradox that there are times when I hear physicists talk about space being part and parcel of the Big Bang expansion, right? So part of inflation is the expansion of space, right?
Right.
That is included within the model, but so I am supposed to have this vision of like that darkness that I envision being on the outside of this field that is expanding. That darkness is technically, in reality, is not existent, right? It's just something that for my it's just a visual aid for the purposes of my understanding to have, right? Like this darkness around this field that is expanding, because that field itself, that is space, right? That is the space in which you find all of the galaxies and so on and so forth, right?
Mm-hmm.
And okay, but see, but then there's also the idea that, or I guess it's non-contradicting. I guess it's really not contradicting, but it's just
pretty contradictory.
Is it?
It is pretty contradictory.
Right, because it is in the sense that they tell you so that is the beginning of space itself. It's within this expansion of the Big Bang. But I guess if you insert one of the many, because there are many, but one of the multiverse models, multiple universes models, there is the model of the child universe, right? But within that model of the child universe, where one of these it's like I forgot, like it pinches off, a universe pinches off from a bigger one.
Mm-hmm.
That bigger one is already a universe where there is infinite space, right?
Right.
And then within that infinite space, this child universe, whatever the technicalities may be and the mechanisms for how they are able to, physicists are able to mathematically describe this thing, because I certainly don't get it. But anyway, apparently they make sense of it to the point where they say this child universe came about. And so this is a child universe with, clearly, of course, we will be talking about a very, very small space that then will expand into infinity, just like the parent universe from which it came from. Right?
Right. So the reason why it's paradoxical, if the universe is expanding, you have to explain what it's expanding into.
Mm-hmm.
That's what makes it paradoxical. Because what is the universe expanding into?
Infinite entropy is what they say. Right?
But there's but then you have two basic and this is the reason why with me, this is why I redefined all of the different things so that I can understand it myself.
Mm-hmm.
And there's two basic schools of thought for our universe. Our universe is everything that exists, and it embodies everything that exists, right? So that's the one school of thought. The other school of thought is that our universe is just one of many parallel universes, right? So with the many,
and you know what? You're completely right about that, because it's very irritating that depending on the physicist that you are listening to at any given moment, is going to have a completely different, different conceptual model, right? It's very irritating that we have to go through this time and time again. Because sometimes, like for example, you mentioned the word existence, and I would assume that model that you have as well of like the universe,
right?
All parallel universes together, right? And then some, whatever the unknown unknown, right? The unknown unknowns. All of that could be part of what you could consider the universe. And then you already know, once in a while you'll listen to some physicists that will just get up in arms about about exclusivity to having a very narrow window of a definition for the universe, only meaning to be the Big Bang model, right? And of course that that just begs the question: well, what are you defining as, or where are you leaving all these parallel universes and so on and so forth? So no, that's a very good point that you bring up.
Yep. So with me, and this is the reason why I made I don't know if you watched Existence is Inside of Non-Existence on my 2 Cent channel, but it's from those two arguments that I came up with the principle that I have, which basically implies there are. So the way that I model the universe, and the way I model existence. So the way I model the Big Bang It's basically like this.
Mhm.
There is only one all-encompassing state of existence, and I define that as omni-existence. Omni-existence is everything that exists. Everything. There is, if it exists, it's inside of omni-existence. Outside of
And
omni-existence.
how do you define existence? Though? Like, would you qualify that conceptual model that some people have of like a nothingness that doesn't even include a quantum field, a quantum state, a wave function, right? Like, or the laws of physics, period. Like, a nothingness that is literally nothingness. Would you consider that part of an omni-existence?
I define omni-existence as axiom perception. Whatever can be perceived exists. And that's pretty much how I define omni-existence. Anything that can be perceived, understood, reasoned, recognized, defined, exists. And all things, all entities which have some state of existence are self-perceiving. So in my definition, an atom is self-perceiving. An electron is self-perceiving. You know, all entities are self-perceiving. That's the most fundamental principle that I use to define existence. All things are self-perceiving, and all perceived things interact with other things that can be perceived. So, omni-existence, and this is the only part that gets a little circular and paradoxical. Omni-existence exists inside of nothingness, and that's nothingness is defined as axiom, no thing, nowhere, no thing, no nothing, non-existence. So everything that we perceive to exist exists inside of a state of non-existence, you know, and that's the only way that it makes sense to me. One thing that humans can exist, there's 5,000 different definitions of God on this planet. Right? There's 5,000 definitions of God. There's only one definition for nothingness. It's universally understood throughout all of humanity. We can all agree on what nothingness means. We can all agree on what zero means. If I said I got $0 in my account, you know exactly what I'm talking about. Like, we all universally understand that, you know. And to me, if omni-existence is where everything exists, but non-existence must exist, then logic dictates that non-existence exists outside of omni-existence, because it can't exist inside of omni-existence, because then it would exist. And it can't not exist because everything exists. Everything must exist. So the logic.
Omni-nothingness? Is that what you called it?
Well, I call it infinite indefinite.
Infinite indefinite.
Yeah, it's the 11th dimension. Infinite indefinite is the 11th dimension, and all dimensions exist inside of infinite indefinite at the 10th dimension. The 10th dimension is omni-existence. Nothingness is infinite, right? Existence is finite, because there's only a finite amount of things that exist in relation to all of the things that don't exist. You know, as crazy as that sounds, there's more things that don't exist when you start to quantify them than there are things that do exist. So when you combine those two together, then you have existence at the very center of non-existence, what is an infinite expanse beyond the 10th dimension. And then dimensionality.
Now, are those dimensions and is omni-existence within the borders of Hilbert space, if there are any.
So, another thing that I started doing recently, and I didn't want to use it. I didn't want to use this term because I didn't want to confuse you. I've been using the term retention to replace dimension because it makes more sense. So space is a
retention.
Space is a retention, and then time is a retention. So we exist in three-dimensional retention and one dimension of time, which I also define as temporal, right? So the 11th, so now the 11th retention will be infinite indefinite, and the 10th retention will be omni-existence. Now, to answer your question about all of the different kinds of space, well, they're just aspects of infinite geometric retention. Does that make sense?
And what is retention as opposed to dimension, or why the difference? What makes it different than dimension?
The difference is that when you use dimension, it has been overly associated with space. So since dimension has been overly associated with space, it's not accurate to convey things beyond space, like time, or any other aspect, any other function. If I wanted to try to describe a fifth dimensional space, well, we can only perceive 3 dimensions of space. So as soon as I say space, you automatically think 3 dimensions. But if I say a fifth retentional geometric volume, well, now your mind is going to try to go beyond just our 3D retention. It's going to try to perceive higher than that, because our fourth dimension is time, right? Whenever they say the fourth dimension, it's associated with time, right?
Correct.
But there's probably four retentions of space, and then 5 retentions of space, and then 6 retentions of space. There's an infinite retentions of space, and there's an infinite retentions of time. So that's the reason why I started using retention.
There's more retentions of space, and
Or,
there's one of time.
say that one more time.
You said there's more retentions of space, and there's only one of time. Is that what you said?
To describe our universe, yeah. To describe our universe, we live in 3 retentions of space and 1 retention of time, and that makes up our 4th retentional space time, right?
Right. That's the black universe, right? As they call it.
Right. So an extra retentional being may live in 4 retentions of space and 1 retention of time. So there's a whole geometric space that they can occupy that we can't perceive. That's what makes them higher dimensional or higher retentional than us. But if you use dimension, then you can't accurately convey that, because if I say 4 dimensions, then you're going to automatically think, 3 dimensions of space and 1 dimension of time. But if I say no, they occupy 4 retentions of space, then you just add an extra coordinate on the Cartesian plane, and then you're halfway there. Now you just have to add that extra retention of time, because in our universe, you can have 3 retentions of space and then 2 retentions of time for time travel. That's how I define time travel. You have that extra dimension there for time travel, and then all of the conflicts of time actually completely vanish with that model, But
if you had 2 dimensions or retentions of time.
Right, you can have an infinite number of retentions of geometry or space, which is why I started using retention, and you can have an infinite number of retentions of time. Does that make sense now?
Yeah.
And that's why I started using. That's why I stopped using dimension and started using retention.
Right. Okay.
And in our universe, and then omni-existence is infinite retention of space and infinite retention of time combine together to create the tenth retention. The tenth retention is the infinity of all of them together. It's just defined as 10 dimensions or 10 retentions to keep it simple, you know. But it could be an infinite number of them, and that's where all of the different types of space that you've learned about, hyperbolic, non-Euclidean, they would just simply fall under geometric retention. You know?
Okay.
All of it goes under geometric retention.
And under your model, what was the 11th dimension or retention?
Our universe retention is three. We
no, but you mentioned 11 retentions
right
within the omniverse, right?
Right. The 11th retention is infinite indefinite. It's all of reality, like all of it. Nothing. It encompasses everything that can and is not. Everything that is and is not exists in our 11th dimension, and everything that is and is not exists within the 11th retention. Everything that is, everything that is exists in the 10th retention, which is omni-existence.
Okay, so the 10th is omni-existence, the 11th is everything that is and it's not.
Yep. Infinite indefinite.
Infinite indefinite. Okay. And now, are these 10? When you say 10, how's it? Why 10? Is that because of string theory?
No. Actually, it's because of infinity. There's an infinite number of infinities, right?
An infinite number of infinities.
Right.
Yep.
Infinity times itself is infinity squared. Infinity times infinity is infinity cubed. Here's the one that's the most mind-boggling. Infinity raised to the power of infinity, right? So when you start getting into that, it's kind of like, okay, that's too much. So what I started doing was I started defining it into a taxonomical hierarchy. So everything that exists is in omni-existence. Everything that doesn't exist is in infinite indefinite. The reason that omni-existence is 10 is because omni-existence is parallel omniverses, and omniverses is 9. Omniverses are parallel multiverses, which is 8. Multiverses are parallel existences, which are 7. And existences are parallel universes, which is 6. And it goes down in that order. Let me make sure that's right, because I know the numbers.
Yeah. Is this in your, and I forgot what you called it. I don't think, I do remember. It's existence and everything that encompasses it.
Yeah, this is, existence and that which encompasses it, yep.
Okay, yeah, because, I've been through so many Facebook accounts that they keep getting deleted, so I always save it, but then I lose it. So
yeah.
If you just add me one more time, that way, now, see, at the time, that was just way too complex to me, but now that I'm a little bit more versed in the, in the subject, I can probably pick out a couple things, better off of it now than I would have in the past. So I would definitely want to take another look at that. And another thing that I was is just this. There's a lot of paradoxes, but without a doubt, okay. So I'll say at the very least, this what has brought a lot of more clarity is the wave function first approach to cosmology that and I don't know if this is only because I'm getting caught up in his model, right, or whatnot, but I cannot also deny that it's not like quantum physics is not the state of the art at the moment. It is, right? Like every the top level guys are they're working on in quantum physics. So, but anyway, within this approach, wave function first approach to trying to understand the existence, I guess you would say, because you do have to use terms like existence more than like the universe, because like you said, a lot of these terms have been overused in the past, and so sometimes when we think of the universe, we just think of like the Big Bang or something like that. So you kind of do have to like redefine some of these things. But anyway, yeah, it definitely, according to that approach, and the hope is there that with that approach, a quantum theory for space-time and general relativity will come about, right? From approaching it from the quantum perspective first, starting off with quantum mechanics rather than with classical mechanics first. And I have indeed personally, I have found it a lot more clear-headed. It's just the fact that God does really get into some very weird, almost like if it wasn't because there's math behind it, you would think that this is stuff that some hippies came up with, right? Like,
right.
During a smoking session or something like that. And the irony that it is physicists now, physicists that are speaking in this manner today. But so a lot of it starts off with Hilbert space, and right there and then, that's already a rabbit hole in itself, because that forced me to have to Google what the hell Hilbert space means, and then when you do that, you find out that Hilbert space is basically like a pocket within the broader concept of is it vortex spaces? Is that what it's called? Or I may be wrong about that term, but it's not vortex space. It's vector spaces, right? So it's vector spaces, and within vector spaces there are normant spaces, and within normant spaces there are inner product spaces. Which of them Hilbert space would be one of them, right?
Yep.
And I have no idea what the hell all of that even means. I don't know how to differentiate a single one because Hilbert space in itself they're already telling me that it's not physical space as we know it. So there's no distance in Hilbert space. So it's like, what the fuck? Like, so what is this? Like, what do you mean, man? So this is clearly like a different dimension, right? Like,
yep. The reason why is because, and this is the reason why, this is the biggest conflict in physics, in quantum physics, and in reality in general, that fails. This is what fails us when it comes to trying to understand the way the universe works. The prime mover, the thing which moves all things, cannot be described mechanically. All motion as we perceive it is perceived mechanically. Something is gonna push or pull, and you don't have a way, even like rocket engines work based off of mechanical motion. Even a thrust vector velocity is requires a mechanical movement. Two objects pushing off of each other to generate some type of motion. If you this is like this is my favorite thought experiment, but probably my least favorite thought experiment because it can't be resolved. If you have a proton and an electron, if you imagine picturing in your head a proton and an electron, with the electron in a classic orbit or as a field going around the electron, around a proton, they're pushing off of each other's fields and interacting gravitationally and moving around and doing all this stuff. All of that makes sense mechanically, right? If you imagine just a proton or an electron by itself in an infinite void, you cannot define a source of locomotion for it. You can't mechanically come up with a way for it to move if it has a localized existence. And that is basically why they create all of these different types of manifolds and different types of space, and because it's the only way that the math shows what motion looks like without a mechanical apparatus pushing on it. You know, I reasoned that the only way an object can be described to move mechanically without a mechanical force is that space has to move mechanically. It's the only way that you can show it, and that's the reason why Einstein said space and time are combined. Think of it like this: if you walk down the street, you're walking with a mechanical motion, right?
Right.
If you walk on a treadmill, your movement is stationary, but you have a net vector force, right? You're moving, even though you can be perceived as being stationary, the math would show that you are moving at 5 miles an hour, right? If you come to rest, then your rest mass will be 0, but you will still have a mechanical force being exerted on you by the treadmill, which is what we perceive as the prime mover. When they do their math, when the physicists do their math, that's the best analogy that I can give you for what they're seeing mathematically. Because you have an object that comes to rest, but then it still has some other force causing it to move, the same way that the treadmill will continue to move you. So they have to create all these different types of space to show how the interactions of the forces create mechanical motion. I don't know if any of that made sense, but
no, yeah. I mean, is there an end to that? I mean, are you just gonna create these different spaces indefinitely?
No, there is no end to it except for Planck's constant. Planck's constant pretty much ended it, because the Planck length is the only length. It's the smallest unit of space that's relevant to our universe. Because at that space, at that distance, there's no longer. You know how when you watch a movie, objects seem to move really smooth across the screen, but if you look at the frames, then you can see that the objects are changing instantaneously. That's what happens at the Planck's length, and that's one of the reasons why I created infinite indefinites. Because at the Planck's length, and I'm probably saying that wrong, I think it's pronounced Planck, but at the Planck's length, objects translocate in space. They go from point A to point C because point B doesn't exist. So if it was a number line, objects would move on either all odd numbers or on all even numbers, because the units in between don't exist. And that's the smallest unit of mechanical motion. So a proton at location A at the Planck's length a proton at location 1 at the Planck's length would move to 3, because 2 doesn't exist. There is no 2. There's only 1, 3, 5, 7, and that's as small as you can go. You know, that's literally how it works. You know,
that's the smallest you can go in regards to what?
In regards to our perceivable universe.
The smallest. Oh, okay. So, how does that apply to like creating these different dimensions or conceptual spaces in order to explain the mechanics of another?
It's very difficult to put in words. Okay, I got it. It's like a clock, right?
Mm-hmm.
If you open up let's say you open up an antique stopwatch and it has a bunch of gears in it, right?
Yep.
You're gonna immediately see the largest gears, right?
You're not what?
You're going to immediately see the largest gears. The biggest gears are the ones that you're going to see that are moving, right?
Yep. Yep.
So you're going to want to know what is causing these gears to move. So as you start taking the larger gears out, you're going to start finding smaller and smaller and smaller gears, right?
Right.
Eventually, you're going to get to a gear, and for the sake of this analogy, it's going to be the smallest gear, but it's going to be attached to a motor, right?
Uh-huh.
When you're looking at all of the different types of space that physicists and quantum physicists are using to describe motion, those are the gears. The different types of space are the gears. The space types themselves get small as the gears get small, right? All we're doing is describing the smallest gears till we get to the actual motor itself. And once we get to the motor, it's going to be smaller than a Planck's length. We're not going to be able to define it because it's going to be smaller than our perceivable ability to recognize. That's ultimately what's going to happen. But it won't matter, because if we can get to the smallest unit of motion, once we know what that is, we can build mechanically all motion from that without having to truly understand how it works. In the same way that we don't understand how motion works, but we can describe a lot of stuff. You know, we technically don't understand motion. We do not. That's the main reason why the Big Bang fails, because we can't explain motion. So we can't explain how the universe started moving. We can't explain how it went from being infinite potential to kinetic, because we can't explain motion.
Even when they talk about, that's what gives me, when they talk about classical mechanics is based off of so you have a state in space, right? Which usually denotes a position of a particle and its velocity through space or in space, right?
Right.
But it's like if it's always moving, where I don't know if I'm even thinking of it correctly. I mean, I guess there is a position, but is there really a position? I mean, there's no position, right? I mean, there's no, you cannot. Well, I guess you know, if you put a grid, if you just design a grid on space, yeah, I guess there is a position. I guess I'm not.
So,
but it's just the fact that what is it like? It's just hard to track, right?
Yeah. So you just actually described the infinite indefinites. Remember earlier when we were talking about the Big Bang and how the singularity was located somewhere? You just touched on the way that I model the Big Bang. And what I mean by that is, if you imagine a Cartesian plane, right? Because that's what you said. Imagine a plane. A Cartesian plane. If you picture one Cartesian plane, right? And then picture a.
Hold on, let me Google that real quick because I don't know what that is. Cartesian plane.
Cartesian plane, yeah.
Oh, I see it. So like an x-axis, y-axis.
Right. So this is so physicists use these to plot vector courses and stuff like that. So it's the foundation that the math is built on. Literally, you're literally looking at the charts that they use with the HLZs. They literally use Cartesian planes. So now, picture one of those, right? Now the one that you're picturing in your head, that is the universe, right? And so at location 0, 0, that's where the singularity is going to be, right?
Right.
Now picture a second Cartesian plane, right? The first Cartesian plane, which is the universe, put that one inside the second Cartesian plane, which is existence, right?
Which is the distance?
Existence. The second Cartesian plane is existence. The first one is the universe with the dot, the singularity in it, right?
Yep.
So the next time you watch a Big Bang video, That's what you that start picturing that. When they show you the little when they show you the screen with all the emptiness and they say that's nothingness,
Yeah.
that's existence. It's a Cartesian plane, right? The second Cartesian, the second Cartesian plane, that's the universe with the singularity in the center, is inside of the first one. But here's the trick: the second Cartesian plane is moving. The universe is moving. Existence is stationary. Does that make sense at all?
Right. So the one with the singularity, that's the one that's moving.
Yep, that one's moving.
Right. And the other one is static.
It's static. Yep, stationary. So the
Right.
universe.
And that will be all the exopasses. Well, the singularity event and our physical universe that we see is just obviously one of these. It's one out of many other possible ways of existing.
Exactly.
Other multi-ways.
Yep.
Right.
And that's pretty much how I perceive the universe. Because you have, like you said, if you have all these things moving around in space,
Yeah.
if there's nothing relative to them, they're stationary. But they're always relative to space. So they're still in motion. Because if they can perceive their own velocity, then they are moving. You know? But I perceive existence as stationary. And relative to existence, the universe is in motion within existence. And that's what we see as the expansion. This is I don't know if I can put this in words yet, but I figured out why the universe is expanding.
Okay.
I don't like. It's really hard to put in words, but basically, imagine anything. Imagine anything moving, right? No. Okay. It will be better for you to imagine a balloon. Imagine a balloon, right?
Mm-hmm.
As it fills with the gas, it expands, right?
Right.
Now imagine if the balloon wasn't being filled with gas, but it was just a physical three-dimensional object moving through space, right? It's just moving, right? It's not getting bigger, it's not getting smaller, it's just moving, right?
Right.
Now, if the universe was an explosion, right? Everything would expand outward, correct?
Yep.
The reason why everything is moving away from everything else is because it's a fourth dimensional explosion. Does that make sense? Let me say it this way. It was a fourth rotational explosion. It exploded in four different coordinates, and so we see we see up, down, left, and right as just part of the fourth rotational explosion, but the actual everything moving away from everything else is actually our fourth rotational vector through our higher dimensional existence. That's why we perceive, when we look up in the sky and we see everything moving away from everything else, that's the direction of the fourth rotation of our explosion. That's what we're seeing. You know,
Right.
when we trace everything backwards, that's why we arrive at a singularity, because we can't understand why everything's moving away from everything else. But that's literally just our universe vectoring in a fourth dimension, a fourth rotation of space. So it's a very difficult thing to describe.
Conceptualized.
Yeah, but it's really elegant. You know, it's very elegant.
Right. Yeah. Now, speaking of trying to conceptualize these things, like, I always try to find pictures that would help me, picture the Big Bang expansion and so on and so forth. And there's different different ones, and I'm not sure that having these different talents, or rather, there should be some kind of I'm not like textbook image for this event, because of the fact that, for example, you see some pictures where it's more of like a cone, right?
Yeah.
A cone where at the narrow point of the cone you have this bright light, this is a white light, right?
Right.
And then as you move towards the broad end of the cone, you have eventually all the galaxies forming and so on and so on, and then eventually you will get like the furthest expansion, black holes having sucked in everything, and now you just have empty space, right?
Right.
And so, in my mind, that's definitely okay. So, in my mind, that seems to have, when they speak of the singularity event of everything being shut in to the size smaller than an atom, minor electron or what have you. When Sean Carroll keeps repeating it, he's done it multiple times, so I have to question it. When he says that the Big Bang is not a location in space, but a moment in time, that I process that as such a paradox, because if you expect me to conceptualize all of the matter in the our universe as condensed to the size smaller than an atom, or I guess that's where my fault comes in, where I automatically think that should be in space, but I shouldn't think of it that way.
So this goes back to why I said I use retention instead of dimension, because his statement is correct. The Big Bang theory is actually more of a moment in time than a location in space. However, it still should be defined as a location in space. So if we go back to the original, remember I had you the thought experiment with the Cartesian planes, remember?
Yep.
So remember, the universe Cartesian plane was inside of the existence Cartesian plane, right?
Right.
Now imagine on the universe Cartesian plane, the singularity expands into the Cartesian plane, right? That's an explosion taking place into a volume of space, right?
So it's just a different kind of space.
Right,
but here our space.
Right, but here's the most important part, and this is the reason why Einstein combined space and time. You can't have movement in space without movement through time. Nothing can move in reality without propagating through time as well, right?
True.
So that's why they're combined. Now, if you believe, or if you accept that the singularity existed in no space because space came from the singularity, then it has to be a retention of nothing but time. So it's a retention of time with no space, right? So the event occurred before there was space. So that's why he says it began as a moment and not a location, because the location didn't exist until after the moment, which is very counterintuitive to the way that we think. But here's how you can understand it. The universe began when it separated from existence. So existence, the universe existed inside of it. Our universe existed inside of existence as a singularity before time began for the universe, in much the same way that a child would exist inside of the womb of a mother before its birth. It still exists, but it exists connected to its mother. So its existence didn't start until birth. So the singularity was the moment of birth for our universe. Before that, it was existence. It was connected to existence in a way that it couldn't be defined as existing in the state as we know it now. So that singularity existed, occupied a location in that stationary, static existence. And then the moment time began for it, it became its own Cartesian plane of the universe, an infinite point in a volume of space as small as an atom, that then expanded infinitely into the dynamic universe. And then if you go back to a Planck's length, at one location of the Planck's length, there was no universe. Then at the next location of the Planck's length, there was a universe. And there's no way to differentiate between those two moments, because at that most smallest infinitesimal scales, even for time, there is no in between. There's only location 1, location 3, and location 2 is the moment between the two, but it's undefined. There is no in between. There's only the universe doesn't exist is true, and then the universe does exist is true. The universe is both existing and not existing. Like that. There is no paradox at that length. So that's how I mean. For me, it works. It's a lot, but that's how I see it.
I mean, it definitely helps. It definitely helps, even if whatever monkey wrenches are thrown. That definitely helps. Put things into perspective. We need some kind of framework. I feel sometimes, right, like when things are getting too scattered.
Yep.
Yeah, so
are you by chance strengthening your math skills at all?
No, I am not, and that's actually the part that I hate about myself right now, because I wish I could understand all of these concepts that physicists talk about in the mathematical terms that they work with them.
So you can understand them. You just have to be willing to do the hard math. You're gonna have to learn. You're going to have to study scientific notation and exponential notation if you want to understand what the physicists are saying. And most of what they do is canceling out variables. Most of what they do is just saying this cancels out to that cancels out to this, and then they show you these really big numbers, but in their heads they're working with values probably within the hundreds of thousands. But that's what you would have to do. You would have to start studying scientific notation and exponential notation.
Exponential.
Yep. Exponential notation is not as widely known, but it's one that physicists use heavily, because it's raising numbers to 10 times the power of 10. So you may have like 1.3 times 10 to the power of 3, and 10 to the power of 3 is 10 times 10 times 10. So then you have so you wind up with like 500,000 or 500 million or something like that. But it's easier to work with because you can get a lot more integers, and unfortunately the universe doesn't like whole numbers. It likes irrational numbers and integers and repeating decimals and stuff like that. So exponential notation helps simplify that stuff a lot.
Okay. There's this very, very good talk among two very very high level physicist. And one of them is not even a physicist. He's a philosopher. David Albert. So it was a conversation between Sean Carroll and David Albert. They did this Science Saturday like podcast, but it was like just a face-to-face thing. Like each of them were in their apartments or homes or whatever, and they were just shooting the shit. Mm-hmm. Right, but you get to like peek into their thinking processes, right? Like, because at this point they're not trying to educate an audience or anything like that. Well, even though they have to step aside for a minute and disambiguate some things for the audience, but they're trying to they're pushing and pulling between their ideas, right? It was very interesting to watch, and obviously Sean Carroll being more of the physicist, and David Albert more of the philosopher. But David Albert was definitely very more sophisticated and picking at the way in which Sean Carroll was bringing about some of these concepts, presenting them rather, and it got to a point where I started understanding what they were actually talking about, right? Because the first time that I watched it, I was completely lost, and then the second time around, I was like, okay, it's more philosophical. It's like you understand things better when you try to tie them into your conceptual models that you have, right? Your philosophy, rather than the very mechanistic way. But then eventually, wherever there is a difference, you're definitely going to come into contact with the opposing view. So anyway, within that, they were talking about how it's almost as if quantum mechanics is a matrix of a denial of facts. It's like it will tell you the probabilities for where an electron may be, right?
So
in space.
So you wanna
go ahead.
What did you say again? It was you said dang it, I had it. You just mentioned it. Well, crap. Is it
the conversation?
Was it the uncertainty principle that you were just speaking on?
A matrix of probability.
Right, matrix of probability. Okay.
Yeah. It's as if it was a matrix of probabilities, but those probabilities are only within a context of what you are asking the theory. So if you're asking the theory what is the probabilities of the electron being in any given position in space, it's going to give you an answer, of course, right? Mm-hmm. If you ask me what is the probabilities of the velocity of the electron in any given moment in time, it will also give you an answer. But that's only because those are the questions that you are asking it, right? But the theory itself is almost a bit where it's denying the fact that there may be a time, or that there may be a space, or there may be a position, or anything for that matter. That's just the information that you're extracting out of it. But it's like a matrix of a denial of facts. There is no space in Hilbert space. There is no time in Hilbert space.
But see, it's a little misleading in the sense that you can use the same analogy, and this is kind of why existence is inside of non-existence. This is why infinite indefinite is both everything that exists and everything that doesn't exist. Because Because you can use that analogy to calculate the probability of an electron being at location A, right?
Mm-hmm.
But you can also use that same equation to calculate the probability that an electron won't be at location A, right?
Right. True.
And you'll still get the same variables, because at some point, even if the probability of it being somewhere is 99.9% out of 0.1%, if you do the math correctly, you will get that. If the probability is high, and you look at it from what is the probability that it'll be true, then you'll get true. It'll be 99% true and 1% false. And if you look at the probability from what is the probability of it being false, then the answer will be it'll be 1% false to 99% true. You know, so
right.
There's a really good duality there. You know, so I think I misunderstood your leading question. I thought you were talking about the Schrodinger cat paradox. The what is it? I forgot. I can't remember exactly what it's called. But basically, the state of uncertainty. Oh yeah, the uncertainty principle. That's what I thought you were talking about. The uncertainty principle.
Oh no. In fact, I'm not too. I mean, it comes up all the time. But what is the uncertainty principle then?
So the uncertainty principle is basically the analogy that we as humans can't know anything. Technically, that's not true. The uncertainty principle is that a thing is
in quantum mechanics, right? There's never the probability is never 100%, and it's never 0%. It's always some number in between, right?
Sort of. The probability is true for both conditions until it's observed. That's what the uncertainty principle means. It means that something is both true and false at the exact same time until it is observed, until it is perceived. You have to falsify a condition for it to be certain.
Right.
Yeah.
Well, that's definitely that's another paradox of quantum mechanics, right? Well, I mean, on one hand, on one hand, there's a language of talking about things being a superposition, right?
Right.
There's a superposition of the cat being dead and being not dead at the same time before you open the box. Right?
Correct.
But then there's also this language using quantum mechanics of probability. So how do they merge those two? Because are they saying that the probability? They're saying that the probability of the cat being dead or alive is 50-50 equally, or are they saying that the probability of the cat being alive is 80%, the probability of the cat being dead is 20%?
It's based on the experiment. So the way the experiment worked, the cat was put in a box with a poison. The poison was hooked up to a trigger that was rigged to a material that had a half-life of 15 minutes. So in 15 minutes, the material with radioactive decay, the trigger mechanism would have a 50% chance of being activated or deactivated or not activated, because only half of the material would emit particles, and so there was a 50% chance that 50% of the particles would trigger the actual device, which would result in the cat's death, or the mechanism would not be triggered. So there was a 50-50 probability of death. And that's what made the cat be both alive and dead at the same time, because they used such a precise triggering mechanism. All things being uncertain, you couldn't absolutely know for certain that the radioactive decay would actually trigger the trap, which would cause the cat to die. That's where the uncertainty was, because you were certain that the material decayed, but you were uncertain if the decay resulted in the death of a cat.
Right.
And that's what made it that, and that's why they called it the uncertainty principle. The only way that you could be absolutely certain that the cat was dead was by opening up the box and looking at the cat.
Right. But see, the Schrodinger's equation tells us though that that before you open the box, the cat was in fact in a superposition of both.
Right.
Being alive, being dead, and being alive, and in fact, this Schrodinger's equation without interruption tells you that when you open the box, there is a superposition. There was a superposition of you seeing the cat being alive, and a superposition of you seeing the cat being dead.
That's what made it so profound. That's what made it so profound, because what it showed was that our existence was uncertain. It showed that if you put your hand on the doorknob, you were in a state of superposition of opening the door and not opening the door. That all of our choices are states of superposition of all the things that we have done and all the things we have not done. Yep.
Yeah.
That's what made.
That's what made his. Right there.
Yep. And that touches on infinite indefinites, because every choice that you make exists in omni-existence, and every choice you don't make exists in infinite indefinites as a choice that was not made, as an event that did not occur. Yep.
Right. Now, where there is entanglement and the system and the observer decohere from meaning that they split from another. They split from the wave function, right, into another branch of what is now another branch of the wave function of you seeing the cat alive, and the cat being alive, and both of you taking the universe with it, because you both become entangled with the universe as well, or the universe becomes entangled with you as well, or vice versa, however you want to look at it, right? But now there's another branch where the opposite happens, right?
Right.
But I guess the branching, I guess, the real branching that physicists must be talking about must be the one that happened at the beginning of our universe, right? Because
in infinite indefinites, what you're describing is parallel universes.
Right.
The branching is what you perceive. That's what the branching is. So, like, okay, so you're wherever you are, right? Let's say you're in your room, and let's say you're thirsty, right?
Right.
And you have a cup of water next to you, right? For every instant that you are thirsty and you do not drink water, you start to branch, right? You perceive yourself as being thirsty, and every instant that you drink water is a branch of you no longer being thirsty.
Right. No. See, that's how I understood it as well. But again, another. I don't know if he misspoke or whatnot. But then again, Sean Carroll said that that the universe is not, doesn't branch, and is not branching every time you make a decision or don't. He's saying that it branches every time there is a particle decay or particles scatter off of each other in some interesting quantum mechanical way, is what he said. Right?
Right.
So,
now, this is what I say. This is what I say.
okay.
We live in a 3-retentional universe with 1 retention of time, right?
Right.
All of that perceived branching that is beyond our perception, that's our 4th retention. If you had the perception to be able to see all things, you would exist at a higher retentional state to where you would see all possibilities occurring. Just like when you look outside and you can see a car going down the street, if you were in a 4th retention, you could look outside and you could see all instances of that car going down the street. The car may have gone down the street, the car may have not gone down the street.
Now, do you really mean this retention or in fact 4? Because
it's 4. Well, I guess technically it would probably be the 5th retention, because the 5th retention is actually change. But it would be the 4th geometric location in our reality, because every aspect that occurs in our 3-dimensional and our three geometric universe occurs in our 3 dimensions. But I'm of the mind that the 4th space is where all of the things that didn't occur. All of the different infinite variables occur on that 4th retention, in that 4th plane. You know.
Right.
And
now, were you going to our conception of seeing ourselves lifting up the cup and not lifting up the cup, does that technically put us in this dimension or 4th?
Yeah, it's what happens in the 4th dimension.
Okay.
Yeah, it's what's occurring in the 4th dimension. Think of it like this: if you're sitting down in your living room and you have someone sitting down there with you, right? If you stand up, they experience you standing up, right? But they may have a perception to where they don't perceive you standing up. They may perceive you as sitting still. And so you are creating a 4th retentional state for yourself of you standing up, which they go with you, and then they create a 4th retentional state of themselves where you're still sitting down, and then you go with them. And so there's these infinite branchings of all of this connectivity, and that's the way I perceive it, you know, because there's an infinite dimension of them. There's a retention of us not on the phone right now because there's an infinite number of all of this going on forever. Because people throw out numbers, because we tend to reject the things that are beyond our ability to comprehend. But we have no problem with using terms like infinity. If there truly is infinite space and infinite time, then there's infinite events occurring within those infinite spaces and those infinite times.
Yeah.
So all possibilities occur.
Yeah, and that would be the only way that would be nice if the universe were that way, because otherwise, with the other options of, for example, having a space that a time that is infinite but a space that is finite, a scenario of that sort would imply that I'm not sure if I mean a space like our space necessarily, or maybe just space in general. Like it could be a Hilbert space or whatever.
Yeah.
In other words, it existence being, or not existence, but experience being finite, but time being infinite, then that gets us into the problem of reoccurring
Yep.
scenarios, right, where things are reoccurring over and over and over again for an infinite amount of time, and that would be a very nice reality to live in, but
it's technically, as you said, it's technically impossible if space is truly infinite.
Well, it would be hard to conceive of time being infinite in a finite space, right?
No, not for me.
No?
No.
Or would you just have different spaces?
No, I'm explaining it in a very elegant way.
Okay.
When space and time are finite, space and time are continuums.
Are continuum.
They're continuums. A circle is a continuum. It's a finite volume that you can move around infinitely, but it's finite, right?
Right.
So the same way that you can move around a circle infinitely, because you will always come back to the original origin and never be limited. If you had a finite amount of time, then the time itself will be reciprocal. So when you start at location 0, or I should say, when you start at 0 degrees at 0 time, once you get to 360 degrees at 360 times, your future simply steps back into the past. You start over.
Yeah.
But you start over at a new position in both space and time, because it's not a circle in the classical sense of the word, but it's a continuum. It's a continuation within a finite container. That's literally what a continuum means. You know?
But that would be an infinite time and a finite space, or that would be a finite space and time.
It will be a finite space and a finite time, because time is going to be reciprocal around itself in the same way that that you can describe a line as a circle, right?
See, but that would be a true equivalent of space and time, right? Where you have an arrow for both, right?
Yep.
Right. That would be a scenario where nothing should stop us from time traveling back in time, right?
The only thing that prevents time travel is the conservation of energy.
Right. Okay. We couldn't necessarily break the circular pattern of repetition, right? But it would just be a scenario where, nonetheless, we would come about the past again.
Right. But I solved the conservation of energy with infinite indefinites. You know, it's a lot of ambiguity, and I know there's no hard math to solidify it in anything.
Right.
But it's a truly elegant system, because the conservation of energy doesn't allow you to travel back in time, because technically the energy if I was to travel back in time, then me as a quantity of energy existing in the present would be destroyed, and then me as a quantity of energy would be created in the past, because I would exist in two separate times in one location, right? Because 37-year-old Paul and 18-year-old Paul would have to exist in the same universe at the same time, right? So me now, my energy will be destroyed now to exist in the past. and then when I go to the past, my energy will be created so that I could exist in the past. So that violates the laws of physics, and that creates that creates a paradox. But if you have two retentions of time, then when I still destroy myself in this retention by moving into a higher retention. So I move from this lower retention of time into a higher retention of time. And when I do that, I transcend this dimension into a higher dimension. When I travel backwards in time, I go backwards in a separate parallel retention of time. So when I arrive in the past, I'm not technically in the past because I'm a higher dimensional being. I can observe the past, but I can't interact with it because I'm in a different retention. And that is what creates the conflict with time travel. Because now you can travel backwards and forward in time, but you can only do it as an observer.
Right, kind of like kind of like in the Interstellar movie.
A little bit, yeah. Yep.
Well, kind of not, right? Because in that case, he was manipulating, like he was interacting with. He was interacting.
He was interacting with gravity, and gravity was being described as a trans-dimensional force. So gravity was transcending the dimensions, and he was able to use that to interact with a lower retention. But he had to violate the laws of physics, because when he programmed that watch with the gravity, he added energy to that universe. He added energy to that moment in time. So the energy that he brought with him from his time, he put that energy into the past. So because it's a good way to remember when you're dealing with energy conservation, is always remember that energy is both the force of the quantitative force and power and fire and all that, but it's also information, because information is the most important aspect of energy. Because remember, science depends on information to derive a reasonable understanding. If you destroy the information, then the science is going to be stopped at that moment. Science can't go beyond that lack of information, not without being ambiguous or biased, or you know what I mean. That's when the uncertainty comes in, and the probability. So
right. Like if tomorrow, an asteroid were to crash and we lost the most vital institutions of that contain information, like libraries and the Pentagon and so on and so forth, we probably have to start off all over again from like the Stone Age, and not knowing how to build computers probably, or none of that. But okay, so okay, and there's another misunderstanding that I have, and you could tell me if it's truly because I'm misunderstanding, or if I am correct in thinking that it's more of a semantic problem. Again, Sean Carroll, because that's the only physicist that I've kind of been just listening to lately for like the past week. He said something to the effect that the real puzzle, when talking about time, is to reconcile how there is an absence of an arrow at the micro fundamental level, and the obvious presence of it in our everyday lives at the macro level, right? So basically, he's saying that if you were the process demon, right? You're familiar with the process demon?
No, I'm not.
So it's basically the so if you roll a die, right? There's a 1 in 6 probability that it will land in any given number, right? Number 2 or number 3 or whatever, right?
Right.
But that's only because you didn't know the exact initial condition
Right.
of the throw, right? And the process demon is that is if you knew the exact state of the universe at any given moment,
I
you can
am familiar with that. Yeah.
Yeah, you can move forward in time or backwards in time, and know anything deterministically, right?
Right.
And that, but more than just that, is that the laws of physics, that the forces at the level of the atom, according to the statement, it doesn't differentiate between the past and the future. It acts the same. So the analogy that he gave was perhaps a better analogy than the one of the dice, because the one of the dice deals more with probabilities. But the better analogy that he gave was if you had billiard balls, and there was just one